I want to go here. And I want to see that today is something, because I had not been planning to do this, but yesterday Professor Nitsure had been talking about continuity and equicontinuity and uniform equicontinuity, uniform boundedness on compact sets. These ideas were there in the topology course that is going on. And it just so happened that Professor Nitsure did that yesterday. And these are the ideas that are actually needed to prove one of these major theorems in complex analysis, which is called the Riemann mapping theorem. Okay, and you will see that actually. So today, what I want to do is begin the proof of this Riemann mapping theorem, and you will see that the ideas that are needed there are basically these ideas that of uniform boundedness, equicontinuity of a family of functions, and it turns out to be beyond equicontinuity for a family of holomorphic functions. And if they're holomorphic, then you can use Cauchy's integral formula. Okay, so we'll come to this in 2 minutes, but the major reason for doing this now at this stage is because, it is just a coincidence that this was not planned, okay? It's just a coincidence that what Professor Nitsure was doing yesterday is exactly what I need today to prove the Riemann mapping theorem. And as I say over and over again, this is sort of showing you that, mathematics is one subject. There are no compartments. There are no watertight compartments in any case. And part of the development that you will see in one part of it is going to be used immediately to prove results in the other. Okay, so let me start with this proof of the Riemann mapping theorem now. Okay, and that's why in the beginning I was going through what Professor Nitsure had done yesterday, and it is the last bit that he was talking about this business about uniform continuity and equicontinuity and uniform. I don't know whether he talked about uniform boundedness on compact sets. Did he do anything like that? Did he mention these terms? Uniform boundedness on compact sets, compact subsets. Had he? Anyone? I think he didn't, but equicontinuity definitely he did. Anyone, do you remember whether he had talked about it?
Uniform boundedness on compact sets, he didn't introduce.
Okay. He didn't. Okay. Anyway,
but
so
there was totally boundedness and equicontinuous family.
Very good. Okay. So we'll see how these ideas are used in the proof of the Riemann mapping theorem. And in fact, in all these things, you must understand that, you're proving these results in topology, in a sort of elementary manner in some sense or the other. They are elementary in some sense, but the motivations for the proofs or motivations of these concepts actually come from complex analysis. The motivation of the proofs or motivation of these concepts actually came from the proof of the Riemann mapping theorem. So one wants to prove something like the Riemann mapping theorem, and for which classes of functions, how do you go about doing this proof? And that is where this idea of uniform continuity, equicontinuity, totally bounded, things like that come from complex analysis. In fact, from the proof of the Riemann mapping theorem and various other things. So it's not that, this is something you must understand, that ideas are coming from different areas and then you're sort of abstracting them out to prove something in, for example, in topology. So what was done yesterday in the topology class, the ideas actually came from proofs of ideas about how to go about proving the Riemann mapping theorem, and so on and so forth. Okay. So I think I should minimize this, and yeah, you can see the screen now, no? Yes, no, you can see the screen, page 71.
Yes, sir. Yes, sir.
Okay. And I just want to remind you of what we had done 2 lectures ago, which is this, I think this is 76 to 82, this is 71. So in this, we had the Schwartz Lemma. What did I do before that? Before that, I did something about this region mapping to that region by a biholomorphic map. Okay, we are going to need all these ideas. Most of these ideas we're going to need in the proof of the Riemann mapping theorem. And we will definitely need this business about Schwartz Lemma. Okay, Schwartz Lemma says that if it is holomorphic, map 0 to 0, then fz in mod is less than mod z. And if at some z0, fz0 is z0, then it is a rotation, and the derivative at 0 is always less than or equal to 1. You will see that this derivative at 0 less than or equal to 1, and derivative of 0 equal to 1 implies f is a rotation. Okay, this idea is going to come up in the proof of the Riemann mapping theorem. Okay, so this is one thing that we will need very definitely, the Schwartz lemma, and you know that the Schwartz lemma is not terribly difficult. It just is a consequence of the simplest version of the maximum modulus theorem. Okay, so Schwartz lemma says something about f from d to d with f0 equal to 0. So if you want to apply this to anything, you must adjust whatever you're thinking about so that it satisfies this condition that it maps from d to d and its value at 0 is 0. Okay. Then here, 60 to 70. This is what? 76 to 82. So this one. Okay. Then in the last lecture, I was talking about this rotations and then automorphisms of the disk. These were particular kinds of Mobius transformations. So this again is going to be needed in the proof of the Riemann mapping theorem. And this is holomorphic in D, and it maps the boundary to the boundary. Okay, this follows immediately. Each of these automorphisms are in fact of order 2. When you apply it twice, you get the identity. Okay, this again I had left it as an exercise. Psi alpha of z is equal to z. So psi alpha inverse is psi alpha. And it's an automorphism of D interchanging 0 and alpha. Okay, and every automorphism of D is of this kind up to a rotation. That e raised to I theta is a rotation. Okay, so the theorem was every automorphism of the disk is of this kind up to that rotation, which is given by e raised to I theta, multiplication by e raised to I theta. So again, this was a consequence of the Schwartz lemma, and quite an easy consequence. Okay. So the only automorphisms that fix the origin are the rotations r theta. Okay. The group of automorphisms acts transitively on D. You've taken this, again we are going to need. In fact, this is the way that Stein and Chakrachi have written this thing. They're doing all these exercises because all these exercises are going to be needed in the proof of the Riemann mapping theorem. Group of automorphisms acts transitively on D, and why? How do we get that? We say that everything in D can be mapped to I. I mean, any point in D can be mapped to I. Okay. And therefore, if you have alpha and beta, you map alpha to I, and you map beta to I. You map alpha to I by a homomorphism phi1, and you map beta to I by a automorphism phi2. And then you take what? You take phi1 composed with on the left phi2 inverse. We'll take alpha to beta. Okay, standard idea. So if there exists a point in which every point can be moved to, then any 2 points can be moved to each other. By the way, I had told you this thing about doubly transitive also. And I don't think that Patil sir has been talking about doubly transitive actions. Okay. Has Patil sir ever talked to you about doubly transitive actions?
So he just mentioned triply transitive actions in
And
somewhere.
what was his definition of triply transitive actions?
No, he just mentioned that
He
some
didn't tell you.
action
Okay.
is present there.
Okay, he didn't tell you what it was. Okay. The idea is the same. Doubly transitive means given 2 points, okay, and given a pair of points and another pair of points, you can find an automorphism which takes this to that and that to that. Okay, each of those points, P1 and P2 going to Q1 and Q2, you must have P1 mapping to Q1 and P2 mapping to Q2 by one automorphism. Anyway, and then of course you have triply transitive things and those kind of. Anyway, so I'm still reviewing what we had done last time. So once you have the automorphisms of the disk, okay, we know how to describe the automorphisms of the disk, and then how we'll get automorphisms of the upper half plane. But we know a biholomorphic map from the upper half plane to the disk, which is given by I minus Z over I plus Z. This is the inverse, okay? And therefore, every automorphism of the disk can be lifted to an automorphism of H. You know, whether it's lift or it is down, it doesn't really matter. And therefore, every automorphism of the disk gives you an automorphism of H. This is the map. It is well defined, and it's a isomorphism of groups. Okay. And then the statement was that if you take ABCD, the SL2R is an automorphism of the upper half plane. Okay. It is not an isomorphism. That map you give is not an isomorphism, but the only things that give the same image are plus minus I. And therefore, you can show that the automorphism group of the upper half plane is SL2R divided by plus minus I, because that's the kernel of that automorphism. And this group is called PSL2R. Somewhere I've written that, I think. Okay. Is an automorphism phi is of the form Fn for some m. This is not particularly difficult. So I've done all this last time. And I have told you also that there are automorphism group of H is SL2R divided by plus minus I, and this thing is called PSL2R. Okay, projective. P is for projective. Anyway, so I had told you that there are these exercises here which are actually connected to very large parts of mathematics, and I hope you will at least try to do these exercises. Okay, they are important exercises, all of them. The exercises in the book of Stein and Shakarchi are really very good, and you will learn a great deal trying to go through these exercises. Okay, so this is where we were last time. I'm sort of repeating myself because it's always good to repeat. Okay, it should come to the stage where you will ask, why is this person repeating himself so much? Questions? Anyone has questions? No, what do? I go here.
Sir, just had a doubt.
Yeah.
So what is this notation SU11?
So that group is also related to all these things. U means unitary. SU11 will mean that you have some 2 by 2 group, okay, which preserves some form. Okay. The form is a form which has 1 plus sign and 1 minus sign. Okay. So you want unitary matrices which satisfy some condition, namely that they preserve the form. What is SO2? Okay. Or SO3? These are 3 by 3 real matrices which preserve the form which has 1, 1, 1 on the diagonal. Okay. So what do I mean by that? Inner product of U times V is equal to U transpose identity V. That means the usual U and V. Okay. So there all the signs are positive. But you know that there are forms which are important which have signs that change. For example, if you have 1 positive sign and 3 negative signs, so what is the inner product of X and Y? they are vectors in R4. The inner product should be x1, y1 minus x2, y2 minus x3, y3 minus x4, y4. So that will be a 1.
3, 1.
Yeah, yeah. Okay. So U11 will mean that you have in that form, you have one positive sign and one negative sign.
Like x1, x2 minus y1, y2.
Yeah, x1, y1 minus x2, y2.
Okay.
That is the inner product.
I was thinking like one double
now
is
you
x1,
have to be
x2
slightly,
and 1.
1 minute. You have to be slightly more careful here. These are over complex numbers. So there's a complex conjugate that comes in there. Okay. So x and y are complex numbers. So the inner product will be x1, y1 bar minus x2, y2 bar, y2 bar. Okay. So in fact, one of the exercises actually talks about this. Okay. And there are these connections between whatever we are doing there. So it's worthwhile going through. That is one of the exercises I've mentioned in that list. Okay. So all these are important groups, and it's worthwhile. I mean, that's what you're beginning to see, that there are connections all over the place, and these groups are important groups. Okay, anything else? No? No. Okay, so what do we want to do?
Also like thinking about R31 semi-direct product with O31, like what short exact sequence I get there actually.
Yeah, I mean, I don't think I can answer such a question that easily. Okay, and these are things that one has to. I mean, the point is, these are things that you should be worrying about, and but first you worry about SU11 and that exercise that is given. Okay, try to understand what that exercise is done. I think it's exercise 4 or 5 in chapter 8 of Stein and Shakarchi. Okay. So yeah, these other questions are also interesting, but you should do those exercises from Stein and Shakarchi first. Okay. Okay. So let's continue now. So I was at this stage last time. So it's taken me nearly half an hour to come to this stage. And now I should go to which one? This one. Now, what did I do? Oh, I closed that. So I have to open it again. Just a moment. Huh? I closed the thing I wanted to open. So just wait. And complex analysis. Okay, can you see the screen now, page 76? Yes?
Yes, sir.
Okay. So this is exactly what Professor Nitsure was doing last time. You have a metric space, and you have the distance on that metric space, and you have a distance between points, and then you have a distance between sets. Okay? So distance, if A and B are subsets of X, the distance between A and B is, by definition, it is the infimum of the distance between A and B, A and A, B and B. Okay? If A and B intersection is empty, what do I want to write there? I think I've written something wrong. If even if I should have written it the other way around. If A and B is empty, anyway, the statement is correct. You can have the distance being 0, okay? If the intersection is empty, does not imply that the distance is 0, okay? And the other way around. What do I want to write there? Anyway, you should be able to figure out what I want to say there. What I've written is not wrong, but I wanted to say that even if the intersection is empty, okay, the distance may be 0. So that is what I've written, okay? Even if the intersection is empty, the distance is 0, and you know that there are examples like this. You would. So what I've written is correct. It's okay. You must play around with this idea a little bit. And then the point is that if you have, what we need is the following, that if K is compact and B is closed, and the intersection is empty, then the distance between K and B is some number delta which is strictly greater than 0. Okay. And why is this true? For each point in that K, there exists a delta which depends on the, for each point K, little k and big K, there exists a delta little k, very bad notation again. Anyway, for each point little k in K, there exists a delta little k greater than 0. That means delta depends on little k. So is that the ball center K 5 delta 5k, sorry, 5 delta k, this ball, this large ball intersection of that closed set is empty. Okay. Then you cover K by ball center K radius delta K. This is a finite subcover. And then this finite subcover will tell you that the distance is at least, you take the minimum of that, okay, and the distance is at least that minimum, or you take the maximum, whatever it is. So you have seen this earlier. Does everyone understand this exercise? If you have a compact set and a closed set, then the distance between the compact set and the closed set is strictly positive. Yes? Is that okay? The distance between a compact set and a closed set is strictly positive. I cannot say this if you have two closed sets which are disjoint. Okay? The distance may be 0. What is the example of two closed sets which are disjoint whose distance is 0? What is the example?
Hello, sir.
Yeah.
The example is in R2 for x
In
greater
R.
0 and y greater 0. Take the curve xy is equal to 1.
Yeah. Yeah, what
And
you're saying is correct, but the easier example is you take integers and you take the set n plus 1 by n. Okay. The set A is the set of integers. The set B is the set of all rational numbers of the form n plus 1 by n. Both these sets are closed and the distance is 0. Okay. So if you have one closed set and one open, the other example you have mentioned is also correct, of course. Okay. But this is the simplest example. Okay. So, but if one is compact and the other is closed, then the distance is positive. Now, the same way of saying this is that if this K that I'm talking about is disjoint from B, that means it's contained in the complement of B. And the complement of B is open. Okay. So the same way of saying this is that if you have a compact set contained in an open set, okay, then the distance of K from the complement of that open set is strictly positive. Okay. Now, let K be compact and K contained in this open set. And this is what I've just said earlier. This is where I needed that. Let delta be greater than 0 be such that the distance between K and, so K is compact. No? So K is supposed to be, so in this picture, K is this line. Okay, that is my K, this business. The distance from K and the complement of omega is 3 delta. Okay, that means if you take any point in K and take this ball around that point of radius 3 delta, okay, you're away from, you're contained completely in omega. Okay, let Z in K, omega in K, and so let delta be a positive number such that the distance between K and the complement of omega, this picture, okay, distance between K and the complement of omega is more than 3K, 3 delta. Take 2 points in K which have a distance which is less than delta, Z and W. Let gamma be the circle around W of radius 2 delta. Okay, then clearly this gamma is contained in that ball of radius 3 delta around Z. Okay. Gamma is contained in omega. Let f be a holomorphic function on omega, and let k prime is something which is larger than k. Okay, distance between all those zetas is the distance between zeta and k is less than or equal to 2 delta. Now, distance between k and the complement of omega is 3 delta. So if the distance between zeta and k is less than 2 delta, then zeta is in omega. K prime is compact. Let B be a bound of f on K prime. F is holomorphic. What did I say there? F is holomorphic. Okay. K prime is compact, subset of omega. You take the bound of f on K prime. So the bound depends on f and it depends on K prime. I should have written that. Huh? I should have written here that the bound, I've written here that the bound depends on the function. What I want is that the bound also depends on K prime. It's not really very important, but anyway, the bound depends on the function and on the compact set K prime. Now f is holomorphic on omega, z and w are there, this gamma is inside that omega, and therefore Cauchy's integral formula says that fz minus f omega is f zeta, zeta minus z, minus f zeta over zeta minus w d zeta. F zeta, zeta minus w over zeta minus. And therefore mod fz minus f omega is, I take a mod inside. I mean, I'm going to pull out this, yeah, maybe I should have been more careful here. I should put the mod inside there, okay? So what is the distance between zeta and z? The distance between zeta and z, what is the distance between zeta and w? It is by definition of delta. That is what your gamma was. Gamma, gamma, gamma. Gamma is a circle around center omega of radius 2 delta. So distance between zeta and w is 2 delta. And distance between zeta and z is at least delta. So I'll get this inequality here. F is bounded by b. Length of the zeta is 2 pi times 2 delta because the radius is delta. And therefore, f is the distance in fz and f omega is this b, which depends on k, and it depends on the function f. Okay. This is an obvious calculation about Cauchy's integral formula, and I'm using this business about distances. So omega is a domain, a family of functions. Now that I was talking about one function, little f. Okay. Now I'm going to talk about a family of functions. That family I'm going to call script f. So omega is a domain, a family of functions script f, which consists of f from omega to c. F is holomorphic. Of holomorphic functions on omega is uniformly bounded on compact subsets of omega. So this is exactly what you were talking about earlier. If for each compact subset of omega, for all k in omega k is compact, there exists a b which depends only on k, such that for all z in k and for all f in omega, fz is less than or equal to b. Okay. So given a compact set, I can find a bound b such that fz is less than or equal to b for all z in k and for all f in f. You know, when you're writing this down, this is again one of those for all and there exists. I think somewhere I made this comment. Okay, for all and there exists and whatever, what depends on what. Okay, for all z in k, for all f in f. Okay, so there exists a b. Yeah, what I've written is correct. For all k in omega, so you have to be careful in which order you're writing these for all, etc. The point is for all K compact, there exists B. Okay. The B depends on K such that for all Z in K and for all F in F, Fz is less than or equal to B. So it should be clear from this statement that the bound B that you're getting, the bound depends on the compact set K. It's uniformly bounded on compact subsets of omega if for all K there exists this constant B, which depends on the compact set K. So that for all Z in K and for all F in F, mod Fz is less than or equal to B. You know, if I interchange the order of this for all, etc., or there exists, the meaning is not the same. Okay? You, as I said over and over again, most students are terrified of quantifiers. And you're not sure how to put those quantifiers in. And this is one example where if you try to write this down, what is the meaning of uniformly bounded on compact sets? You know, there's a very good chance that you will write it wrongly. So for all K, there exists a constant B which depends on K such that for all Z in K and for all F in F, Fz is less than or equal to B. Okay? The family F is said to be equicontinuous on a compact subset of omega if equicontinuous on a compact subset K of omega. So K is fixed. Okay. So the function, the family F is equicontinuous on a compact subset of omega if for all epsilon greater than 0, there exists a delta greater than 0, which depends on K, such that for all Z and W in K, Z minus W less than delta implies Fz minus Fw is less than epsilon. Okay. And this, I'm sure, this is equicontinuous on a compact subset of K. So you're fixing the compact subset of K. Then for all epsilon, there exists a delta which depends on K, such that for all Z and W in K, mod Z minus W less than delta implies Fz minus Fw. So I should have written here. I have not written it completely correctly. I should have written, please note this, please note this, that I should have been more careful here. Page 77 at the bottom, I should have written, for all epsilon greater than 0, there exists a delta greater than 0, which depends on K, such that for all Z and W in K, for all F in F, script F, for all little f in script F. I have not written that for all little f in script F. Okay. Please note this at the end of page 77. I should have for all Z and W in K and for all F in F. Okay. What I'm saying is that the delta works for all F in F. For all Z and W in K and for all F in F, Z minus W less than delta implies Fz minus Fw is less than epsilon. So as you can see, I have been not quite as precise as I should have been. So here you must add for all f, little f in script F. So what does this part A, what does this inequality say? Okay. The thing is the f that you wanted, when I was doing this, f was a fixed f. Okay. Gamma is a compact set. Okay. And therefore what you will get is that this Z minus W less than Fz minus F, Z minus W less than delta for all F in F, then Fz minus Fw, where do I have it here? Fz minus Fw is less than this quantity. So if Z minus W is less than epsilon, okay, then Fz minus Fw is small. fz z minus w less than some delta 1, then fz minus fw is also small. Okay, and this is true for all f, because here the bound b was a bound for the single f. But the same bound b, you can find a bound b which is true for all the f's. Okay, so what we have proved there is that this statement is true for all the f's, because all the f's are uniformly bounded, okay, on compact sets. So equicontinuous means uniform continuity uniformly in the family. And so what is that thing that we have just proved for one function? That inequality holds for all functions in that family, because the family is uniformly bounded on compact subsets. Okay, uniformly bounded on compact subsets. You can find this bound B which holds for all f. Okay, so here I should have for all f. That bound is for all f, and therefore we get this theorem. If f is a family of holomorphic functions that are uniformly bounded on compact subsets of omega, then f is equicontinuous on every compact subset of omega. Okay, because you can find this bound for any compact subset of omega. So f is uniformly bounded on compact subsets. The bound can be chosen independent of the f, and this holds for all f and f. This gives equicontinuity. Okay, so this is part of Montel's theorem, that an a family of holomorphic functions that is uniformly bounded on compact subsets is equicontinuous on every compact subset of omega. Okay. There's still something to be done there, some gap there, which you should try to understand whether the statement is correct. Okay. I have left one gap out. Try to figure out what that gap is. Okay. So now you see we are doing something for each compact subset. We want to have these compact sets to be growing in some manner. And I think I talked about this some time ago. Okay. And I was slightly confused at that time, but then finally I said the right thing. Let omega be open. There is a sequence of compact subsets Kn contained in omega. Each Kn is compact. Each Kn is contained in the interior of Kn plus 1, and the union of Kn is omega. Okay, this is exactly what I wanted. I think I talked about this some time ago, and then I left it as an exercise to see what you have. How do you prove this? So what do? You take Kns, should be getting bigger and bigger. They must be compact, and they must be sort of filling out the open set omega. Okay, that means if they're filling out omega, then the distance between the compact set and the complement of omega should be going on and on decreasing. Okay, so the first thing should be far away from the complement of omega. The next one should be closer to the complement of omega. The third one should be even closer to the complement of omega, and so on. And if you just think about this, you'll see that Kns should be all those points whose distance from the complement of omega is greater than 1 by n, greater than or equal to. So this becomes a closed set. You want it to be compact, so you make it bounded. Okay, and I wrote something wrong there, but you want K to be z in omega such that the distance between z and the complement of omega is greater than 1 by n. And then you want to make it bounded, so you intersect it with ball center 0, radius n, its closure. So Kn is closed and bounded, and therefore it is compact. Kn is contained in the interior of Kn plus 1. This is an exercise, okay? And the union of Kn is the whole of omega. Such a family is called an exhaustion of the open set omega. And therefore, if you have this, then you see if you take any compact set now, this Kns are a fixed family of compact subsets of omega. Okay, Now I take any compact subset C of omega. Interiors of Kns form an open covering of C. Therefore, this open covering interior Kns has a finite subcover. Call that interior Kn1 union interior Kn2 union interior Kn3 and so on. But these interiors are increasing. And therefore, you can take a n which is greater than any of these n's. And then you will get that K is contained in that K sub big N. Okay, so the property of this family is that even though this is a fixed family, the property of this family is that if K is any compact subset of omega, then K is contained in K sub n for all n greater than or equal to some n naught. Okay. I mean, if it's contained in one Kn, it is contained in every Kn greater than that particular Kn. Okay. So you only have to choose one. Such a family is called an exhaustion of the open set. If you have a domain and you have a family of holomorphic functions on the domain, F is a normal family if every sequence of functions in F, every sequence, it's a sequence in F. That means it's a sequence of functions in F. So every sequence has a subsequence which converges uniformly on every compact subset of omega. Okay? And the limit it converges to need not be in the family F. Let me say this again. A family is a normal family if every sequence in F has a convergent subsequence which converges uniformly on every compact subset K of omega. The limit function need not be in that family. So the exercise here is write down an epsilon delta for all there exists statement. Okay. And again, let me assure you that 95% of you will not write this correctly in the initial thing. And then you have to realize where you're making a mistake. Okay. In the same way that on the previous page, I've told you something that I made a mistake and I read it, I realized it here. Okay, page 77 or whatever it was. I realized it when I was reading it that I should write here for all F in F. Okay. The same way, you please write down the definition of a normal family. Okay. Every sequence in F has a subsequence which converges uniformly on every compact subset of K. This every compact subset is what is important here. And in fact, had you said this in the, was this talked about in the topology class? I mean, topology, obviously, you're not talking about normal. Okay. I mean, you're not, sorry, you will talk about normal. You're not talking about holomorphic. But was this idea introduced in the topology class yesterday? Yes or no? No one is answering, so I don't know if anyone is there or not. That I remember. Yeah? Yes, was this talked about yesterday?
I think no, sir. He only talked about equicontinuous family and
Ah, yeah, I think it may not be talked about, but anyway, the point here is that, of course, Nitzer sir would not have talked about holomorphicity, but this idea that, something as family of functions such that every sequence has a subsequence which converges uniformly on every compact subset. Okay, so such a thing is called a normal family. And I hope I've asked you to do this once earlier, that write down epsilon delta definition. And I mean, that time also, one of you had given the right epsilon delta statement, which I don't really count because I had probably taught that person earlier. But anyway, it's good that he can write it down. So here also, please try to, again, let me tell you this, please try to write down an epsilon delta for all there exists version of this statement, this definition. F is a normal family if for all something, for all epsilon, for all subsequences, there exists a subsequence for all compact sets which converges, that convergence need not be in F, etc., etc. Okay, so please write down an epsilon delta for all there exists statement which defines what is a normal family. So, if F is a family of holomorphic functions that is uniformly bounded on compact subsets of omega, then F is a normal family. Okay. Now, the idea you have seen earlier. Okay. Omega is an open subset of C. Therefore, there exists a countable dense set. It's a separable set. It's separable. Omega is separable. So there exists a countable dense set. Yeah. And in fact, you know a countable dense set in omega. Namely, you take all the rationals that are in omega. Okay. The rationals are dense. You take the rationals in omega, subset of C. So what I mean is both the real and imaginary parts are rational. That's a countable set. And it's dense. So let Wj be a countable dense set in omega. It doesn't really matter which one you choose. Okay. Now, what do you want to show? We have F is uniformly bounded. So you want to show it's a normal family. Normal family means that every sequence of functions has a subsequence which converges uniformly, and you want it to be on every compact subset of omega. So first, you fix a compact subset K of omega. So this the first thing I'm doing is for a fixed compact subset of omega. Fn is uniformly bounded on K. So you pick the point W1. Fn W1 is bounded. Therefore, every bounded sequence has a convergent subsequence. So Fn1 is a subsequence of Fn such that Fn1 omega 1 converges. Now you look at omega 2. Fn1 omega 2 is a bounded sequence. Why? Because you have this uniform bound. So there exists a subsequence Fn2 of Fn1 such that Fn2 of omega 2 converges. Notice that Fn2 of omega 1, Fn2 is a subsequence of Fn1, Fn1 of omega 1 converges, therefore Fn2 of omega 1 converges. You continue in this manner. So there is a subsequence Fnr of Fnr minus 1, so that Fnr of omega r converges, and Fnr of omega j converges for all j less than or equal to r. Okay? Take the diagonal. This is called the diagonalization procedure. take the diagonal thing, which is Gn is Fnn. Then obviously Gn of omega j converges for each j. Okay, because as soon as this first n is greater than j, okay, as soon as this n is greater than j, then Fn k converges for at omega j. Okay, so you have convergence. So now we have already proved that if you have something that is uniformly bounded on compact sets, then we have proved that it is equicontinuous. F is equicontinuous on every compact subset of omega. Remember, the k is fixed. The claim is that Gn converges uniformly on k. The family is equicontinuous. So I've told you what this equicontinuous is. Okay. For all epsilon greater than 0, for all there exists delta greater than 0. Here I've written it correctly. Okay. So I shouldn't feel that bad. For all z and omega in k, as usual, I did not write it there. Then I realized I should write it. For all z omega in k, for all f and f, z minus w less than delta implies fz minus fw is less than. I've written for all f and f again there, but you should, maybe I should say this right now. You should try to put all the quantifiers you're trying to use in the beginning. When we speak of something in the way that natural language works, you can put the quantifier at the end also. Okay, so what do I mean? So it is not really wrong to put it in the end, but there's a certain interpretation that is going on there. Okay, and the interpretation is that even though you write for all f and f at the end, what you mean is that for all f and f is in the beginning. For all z and w and k, for all f and f, z minus w less than delta implies fz minus fw is less than epsilon. Okay. How should I explain this? Quantifiers can be also put at the end, but you should try to avoid doing that. The quantifiers should always, you should try to put all your quantifiers in the beginning. So nearly time. So you please give me an example where what I'm saying is properly illustrated. I don't want to put for all f and f at the end of that statement. I should be putting for all f and f in the beginning of that statement. Okay. And it should make a difference in the meaning. So, what I'm telling you is something of the following kind. Okay. And this is part of that Star Wars movies. Yoda used to say, what did he say? When he wants to say that all elephants have yellow ears. What did Yoda say? Yes?
Ears, all elephants do.
All elephants have yellow ears. What would Yoda say for that?
Have yellow ears, all elephants do.
Do you understand what I'm trying to say?
Yeah.
I mean, we would say all elephants have yellow ears. Whereas Yoda would say, yellow ears have all elephants. Yes? I hope all of you have seen this Star Wars business and you know what I'm talking about. Okay? And there's nothing wrong in saying that yellow ears have all elephants. Okay. But we really don't want to talk in that manner. Yes, we are not all Yoda. Okay. So keep the heart. So I think this is a good example. Maybe we just stop on that. And people who have not seen Star Wars should get some of the very nice lines that Yoda has. Yellow ears, all elephants do. No, what yellow ears? What? All elephants have yellow ears. So yellow ears, all elephants have. No, what did you just say? Who was this? Ishad, you said something, no? Who said it?
I to the sentence.
Ha.
I said, have yellow ears, all elephants do.
Ha. Ha. That is correct. Okay. Have yellow ears, all elephants do. Okay. Now, this is actually, if you think about it, okay, in Hindi, what do you say? Or Marathi, what would you say for this? Okay. सब हत्ती के पास पीले कान हैं. Whereas पीले कान है सब हत्तियों के पास. In Hindi or Marathi, in any of the Sanskrit languages, it doesn't really matter. Do you understand what I'm trying to say?
Yeah, that's very interesting that it doesn't matter in those languages.
In the Indian languages, it doesn't matter. Whereas in the Western languages, it does. Okay? And this is part of the reason why Sanskrit is supposed to be so useful in computer science. Okay?
Oh, really? So Sanskrit is used in computer science?
I mean, this idea, this grammar is why people are very interested in Sanskrit when they're doing computer science. Okay? It doesn't matter in grammar where the verb and the subject goes. Yes? Okay?
Yeah.
Whereas in, you can say it in both ways. हर हत्ती के पीले कान है हर हत्ती के, or whatever, that kind of business. So whereas in English, Yoda is not speaking proper English. Whereas if you say it in Hindi, you are speaking proper Hindi or Marathi or whatever. Okay. So anyway, that is, by the way, those of you who don't know what I'm talking about, please find out what I'm talking about. And you must be careful that your quantifiers, as much as you can, your quantifiers should be in the beginning. Okay. And if you can come up with an even better example than elephants having yellow ears, you please tell me next time. Okay.
Yeah, I can tell you now.
Yeah, tell me. Yeah.
This is, he says, into exile I must go, failed have I.
Mm-hmm. Very good.
This is the third film.
Oh, is it?
He has failed to defeat Palpatine.
Okay. Good. That's exactly what I mean. Okay. So be careful with where you put your quantifiers. Okay, so we stop now. It's 4:30. It's past 4:30, so I should stop now. So we meet again on Monday. Any questions? So homework